Okay, so at this point we're going to launch into our study of time-dependent phenomena, and this is going to be very fruitful. We're going to develop a whole lot of new results and new ideas that will lead us to wave propagation. They'll lead us to the theoretical result that the speed of light is independent of the frame of the observer. This is the basic result behind special relativity. And the results that we're going to derive in the next few lectures are going to be both of fundamental importance to physics, but also practical importance to a great deal of technology. Okay, so when we launched into our discussion of electrostatics, we based our discussion on the following observation. Okay, so our whole discussion was based around the observation that if we have two charges separated by a distance, mod r1 minus r2, that the force of one charge on the other charge decreases the square of the distance between them, that the force operates along the line of the line joining the two charges, and that the force is proportional to the product of the charges. We developed everything in electrostatics from that observation. Similarly, when we went to magnetostatics, we developed all of magnetostatics on the following experiment. Okay, so in magnetostatics, we looked at two current elements. This one here, I1 dl1, this one here, I2 dl2, and the force of one current element on the other one was given by this relationship. This result, or this formula, was consistent with experiments that we would do in the real world. Okay, so in other words, everything we've done so far is to make an observation in the real world and then write a theory that describes that. And all right, we're going to, this of course is one of the foundations of the way we do science, and we're going to do the same thing with dynamic behavior, or the same thing with time-dependent phenomena. And the experiment we're going to study looks as follows. Okay, we have three experiments, and all the three experiments are similar in the way they've been set up. We have a square region here where we have a magnetic field going into the board. This is the same in all three cases. And we also have a loop of wire with a resistor. And, okay, in this regard, all these experiments are the same. But in experiment 1, we're going to pull the loop of wire. We're going to pull this loop out, away from this magnetic, and so of course the amount of magnetic flux cutting that loop decreases. So there is magnetic field within this region here and none outside the square. All right, so the observation in this case is that we get a current. A current flows in this wire like this when we pull this loop out. Okay, very interesting. Well, in this frame, what we have is we have a magnetic field, and that magnetic field produces forces on the charges inside the wire. So remember that we have the Lorentz force law. F is equal to QE plus V cross B. Well, evidently there are no electric fields in the problem, so we'll get rid of this, which means the only force available to us is the magnetic force, and this drives a current. All right, so a straightforward observation. If, however, we leave the current loop where it is and we pull the magnetic field away, then, not surprisingly, at least to us because we understand relativity, exactly the same thing happens. We drive a current in this wire here, and everything we observe about that current is precisely as we observed in this experiment. All right? So we're now going to pull this away in that direction. And again, in both cases, let's pull it away at speed v. And in this case, if we think about the force law, well, we know that F is equal to QE Well, this is rather interesting, because in this case the velocity, that is the velocity of the charges, is zero. So this term is zero, and so we're left with the observation that there must be an electric field that has entered, at least in the rest frame of the loop. So there must now be an electric field. And in this third experiment, what we're going to do is we're going to let the magnetic field be a function of time, and let's let dB dt be negative. We'll have it being less than zero, and once again we get exactly the same current flowing through the wire. So what we have then is, apparently we have electric fields that are being generated as a result of the change in the magnetic flux, that is the change of the integral of B dot dA that threads our wire loop with the resistor. And we need to be able to write down an equation which is consistent with our observations. So the current that is flowing in the wire, flowing in here, is going to be proportional to the integral of E dot dl around that closed loop, and furthermore the current that is flowing through the wire is observed to be proportional to the time derivative, or the negative time derivative, of the magnetic flux threading the loop. So let's write that down as a mathematical law. Alright, so this would be consistent with the observations that we make in those three experiments. And this is the key new piece of information that we're going to include. I can now use Stokes' theorem to rewrite the electric field equation in the following way. Okay, so we have rewritten the electric field, we've rewritten the integral around the loop, integral of E dot dl, as a surface integral using Stokes' theorem. So we have an integral of curl of E dot dA and integral of B dot dA. These are over the same area, so now we can peel off that integral, and we have curl of E is equal to minus dB dt. Now you'll notice that when we have time-independent phenomena, we wind up with curl of E is equal to zero, which is completely consistent with electrostatics. But when we have time-varying magnetic fields of any form, we're going to have to include that time variation of the field in the curl equation for E to be consistent with the three experiments that we just wrote down. And this is the new addition that we have here to our Maxwell's equation, and this Maxwell equation is now correct. It's correct in the sense that it's consistent with all the observations we make. It's consistent with electrostatics, where the curl of E is zero. It's also consistent with dynamics when we have a time-varying magnetic field. In a few lectures' time, we're going to see also a change, an analogous change to our equation for the curl of B. That's going to involve time derivatives of the electric field. Okay, but for the time being, we're going to concentrate on this result.